Hello, good afternoon. Can you hear me?
Yes.
Okay, good afternoon to all. My name is Larisa Mocanu and I'm a PhD student at the University of Cassino in Italy. And the work presented today is focused on the influence of powder recycling on the fatigue crack growth propagation in titanium samples produced with the electron beam melting process. This work is a collaboration between us from the University of Cassino, the University of Calabria, and the Research Center SIRA. In this presentation, I'm gonna introduce briefly the topic, then I'm gonna show you the goals of this research activity, and then also I wanted to illustrate some of our previous results from our previous works. And then I'm gonna start with the results, the materials and methods, and the results of this particular topic, which is the fatigue crack propagation in the titanium samples. So, as is known, the electron beam melting process starts with a metal powder as the material feedstock, which is previously atomized. If it's a virgin powder, then it's previously atomized according to one of the several existing methods. And then after the manufacturing process, we will obtain the desired components and a certain amount of waste powder. Also here, the waste powder is highlighted. And in order to keep low the production cost and to improve the process efficiency, it is possible to reuse this waste powder in the next manufacturing cycle. So this waste powder can be firstly sieved in order to narrow the particle dimensions, and also to eliminate any elongated particles, bonded particles, and so on. And then it is also possible, but not mandatory, to mix this sieved waste powder with other virgin powder, for example, to keep low the oxygen content. And then starting with this mixed powder, another manufacturing cycle will start, and at the end of which we will obtain other components and, of course, other waste powder. So here I want to highlight that these components and these components are maybe different because the material feedstock, of course, the initial material feedstock, it's different. And also this virgin powder may be different from this waste powder and from this waste powder because inside the EBM chamber, it may be some degradations. So in this work, we analyzed 3 sets of components produced with the electron beam melting. And these components were produced starting with the 3 batches of powder particles, of titanium powder particles. The first one is the batch A, which is a powder recycled more than 100 times. Then we have the batch B, which is a powder recycled 5 times. And in this case, at each cycle, this LE powder was added in order to keep low the oxygen content. And then we have the batch C, which is the virgin powder produced by this company according to their advanced plasma atomization process. So for each of this batch, several different components were produced with the electron beam melting process. And in this work, we focused on these plates here, this plate. And here there is a more detailed view because I wanted to highlight that the building direction is along the z-axis. Then each plate was then sectioned in order to obtain 4 compact tension samples for each plate, and in order to have the crack length perpendicular to building direction. And then all of these samples were subjected to the crack growth propagation test using this Instron 10,000 fatigue machine. Here below, I also wanted to highlight that the powder recycled more than 100 times, which is the batch A, exceeded the oxygen limit according to this ASTM for the aerospace field. So this is detrimental for these powders. And here there are some results from our previous work. We investigated the morphology and the external and internal defects of the powders. And here we can clearly see some differences between the virgin powders and the other two recycled powders. First of all, we have all of these tiny particles, which are called satellites. And this is detrimental for the powders because the flowability is decreased. And but at the same time, we have almost spherical shape and a surface almost smooth. While regarding the recycled powder, the type B, we have a middle situation, while for the type A, which is the powder recycled more than 100 times, we have a clearly degradation of the particles. We have irregular shapes and also tiny particles bonded on the surface of the larger ones, also some elongated particles, some broken particles, and so on. So we have a clearly degradation with increasing the recycling numbers of the powders. Regarding the internal porosity, we saw that the virgin powders had a higher amount of this internal porosity, and this is due to the gas entrapped in the particles itself during the atomization process. And this tiny porosity inside the powder particles was decreased in the two recycled batches of powders, and this is probably due to the preheating inside the EBM chamber. Regarding the microstructure, we saw differences regarding the quartz-enaid microstructure here in the batch A and the batch B. And this is probably due to the slower cooling rate during the production process, while regarding the virgin powder, due to the higher cooling rate during the atomization process, we have a microstructure mostly martensitic. Another interesting thing is this alpha case, which was observed only in the two recycled powders. And this alpha case is a layer rich in oxygen around the particles, which is also brittle and harder than the core. But this needs to be properly investigated. We also investigated the defects inside the components produced with the electron beam melting process, and we saw no particular difference between the three kinds of components. We saw that all of the components investigated showed the classical defects, which are typical of the electron beam melting process, which are these macropores, this tiny porosity, the roughness surface, and of course the lack of fusion. And all of these defects are mainly due to the process parameters and not to the recycling processes. Regarding the microstructure, no particular differences was observed between the three kinds of components. They exhibit mostly a basket wave microstructure. And something interesting was this prior beta grains, which tend to follow the building direction, but this was observed only in the center of the component, and close to the surface, this was not observed. This also was observed in all of the three components. So also here the influence of the recycling is not visible. We also investigate the influence of recycling on the fatigue properties. We performed some fatigue tests on the three sets of components. And we also here we saw no particular relevance about the recycling processes. Here in this first graph, we saw that the stress nominal range versus the number of cycles, we saw no particular difference between the three types of components. The only difference we saw is that the data scatter is quite high, and this is probably due to the high amount of defects inside the components. We performed also the fracture surfaces, and we saw that all of the components were characterized by a higher amount of lack of fusion defects, and the crack starts from one of these lack of fusion defects, which is a process parameters related defect, and it is not due to the recycling strategies. We also performed here a defect influence according to Murakami method, and we analyzed the external defect and also the internal defects, and we saw a slightly difference between the average dimension of the critical defects, and it is higher with increasing the number of recycling, as can be seen here, the comparison between the A type with the virgin type. And but in this case, we saw also decrease in the data scatter, as can be seen here. But also in this case, these are preliminary results, so we need to investigate better this topic. So regarding this presentation, the crack growth propagation behavior, we investigated 3 kinds of samples: sample A, sample B, and sample C. And we here is displayed the CT sample, and here there are the dimensions. Then we performed this fatigue crack propagation test using this Instron 1000 machine, and here are displayed the characteristics of the test. And then we monitored the crack length using the DIC. Here on the right, we also can see an interesting moment when the sample reaches the final fracture. Of course, this is not the real speed of the test. I just wanted to highlight this moment. And here are the results. So we saw from this crack propagation rate versus stress intensity that there was no particular difference between all of these 3 components analyzed. And the results are similar to each other. While regarding the normalized crack length versus the number of cycles, we saw small difference between the sample C, which seems to have a greater resistance to the crack growth propagation, but also in this case, this difference is minimal. And we also investigated the fracture surfaces of these components after the final fracture, and we saw no relevant differences between the 3 types of components. I just wanted to highlight here the classical fatigue striation. Also, in this case, these components are characterized by a high amount of internal defects, such as these voids. And we also saw some secondary cracks, but this was observed in all the components analyzed. So also in this case, particular influence of the recycling strategy was not observed. And I also wanted to highlight that there was a transition from this fracture mode, which is more ductile in this area, closer to the first steps of the crack propagation stage, while approaching the area closer to the final fracture, this fracture mode, there is a transition between this ductile mode to a mixed mode, brittle mode and a ductile mode. But also in this case, this was observed for all the 3 kinds of components. So also in this case, relevant influence of the recycling processes was not observed. So in the conclusion, in this work, we analyzed the effect of powder recycling on the fatigue crack propagation behavior on these titanium components produced with the electron beam melting. And these components were produced starting with 3 batches of powder. So we have the recycled powder more than 100 cycles, which is the type A, the recycled powder 5 times, which is the type B, and the virgin powder, which is the type C. And we saw that there was no particular differences between the 3 samples investigated, because all of these 3 samples showed the similar behavior. Slightly difference was observed in the type C component, which is the virgin one, although this difference was minimal. Regarding the fracture surfaces, we observed a high level of porosity. This porosity and the defects are mainly due to the process parameters of the electron beam melting machine, so they are not related to the recycling processes. And also, we observed the transition of the fractal mode from ductile to a mixed mode of ductile brittle in all the three kinds of specimen. And also in this case, as I said, there was no particular difference, a relevant difference regarding the recycling processes. So thank you for your attention.
We have time for just one short question.
Quick question. It appears that you mentioned several times that the data appeared to result from process parameters in the E-beam manufacturing process. So in a hypothetical situation, if you could optimize the build parameters, do you and thereby mitigate the errors that you're finding in the microstructure, do you think that recycling will have an effect on the fatigue crack growth rate based upon what you've seen?
Maybe the optimization of the process parameters. Yes, I think if we could optimize these process parameters, we would see the effect of recycling better. So I think, yes, maybe it will be some differences from the crack propagation point of view, because as I illustrated before, from the powder point of view, we have clear differences between the virgin powder and the recycled ones. So I think all of these defects already inside the powder can be transferred to the components. So if the process parameter could be optimized today better, I think, yes, the recycling processes could degrade the crack propagation resistance in the recycling components.
Thank you. I think there is still one other question to be made.
Good afternoon. Congratulations for your nice work,
Thank
great
you.
work. My thought is about when you talk about 5 times of recycle. When you this raw material, recycled material that you use is only recycle, or there is a percentage of new material? Because normally you use the recycle with new materials, and we have a percentage. It was the case or not? It's the raw material for the specimen that was 5 times is only recycle, or you have both materials? Because in the recycle cycle, we put some percentage of new material and some recycled material.
Yes, if I understood, did you ask if the BHP, which is the powder recycled 5 times, have some new powder? Yes, yes. At each cycle, we added this LE powder, which is it's basically the same titanium alloy, but it's grade 23 because we wanted to keep low the oxygen content, because this alloy is characterized by a lower oxygen content. Because we know from the literature that we have this problem. As increasing the recycling cycles, we have an increasing in the oxygen content.
Okay, thank you.